Welcome to The Explainer. Today, we're going to learn to see the invisible. Seriously, we're going to uncover this hidden architecture of forces that holds up, well, everything, from the tallest skyscraper to the very chair you're sitting in right now. So let's kick things off with a puzzle that engineers have to solve pretty much every single day. You've got two people pulling on this bolt, but from different angles. Where does it actually go? And just how strong is that combined pull? That is exactly the question we're going to answer. Now, the answer isn't as simple as just, splitting the difference. By the time we're done here, you'll know exactly how to find what engineers call the resultant force, which is just a fancy way of saying that one single arrow that perfectly represents the combined effort of all the others. So here's our game plan for building this problem-solving toolkit. We'll start by figuring out how forces team up. Then we'll use some simple geometry to visualize them. After that, we're going to break them down with a little bit of math, understand the incredible power of rotation, and finally put it all together into one powerful method. Okay, first things first. Before we can solve anything, we gotta speak the language, right? We need to define what a system of forces even is and learn how to classify the different ways they can all interact. This is our foundation. So anytime you have more than one force acting on an object, you've got yourself a system of forces. And the most important thing to remember here is that every force is a vector. That means it's not just about how strong it is, it's also about the direction it's going and exactly where it's being applied. One of the first ways we sort these forces out is by checking if they're on the same plane. Think of it like this. If you can draw all the forces on a single, flat sheet of paper, then they're coplanar. Easy enough. Now, what if you could draw a line through all those forces and all those lines cross at one single point? We call those concurrent. A perfect example is a bunch of ropes all pulling on the same hook. And if the forces are running alongside each other like train tracks and they never ever intersect, yep, you guessed it, they're parallel forces. They can be going in the same direction or opposite directions, but the key is they never cross. All right, now that we've got the vocabulary down, let's grab our very first tool. And believe it or not, it's basically just a pencil and a ruler. We can literally draw the answer to these force problems. Our first method is this really clever geometric trick called the Law of the Parallelogram. It's a surprisingly simple and visual way to find that single resultant force we were talking about earlier. So here's how it works. You just draw your two forces, P and Q, starting from the exact same point. Then you complete the parallelogram around them. See that diagonal that cuts right through the middle, R? That's it. That's your answer. That's the resultant force, showing you both its strength and its direction. Okay, that's cool for two forces, but what if you have three, or four, or more? The idea is exactly the same. You just chain the arrows together, connecting them head to tail. The one single line that closes the whole shape, from the very start to the very end, that's your resultant. We call this the Law of Polygons. Now, drawing is fantastic for getting a feel for the problem, for visualizing it. But for real-world engineering, building a bridge that won't collapse, you need precision. So now we need to bring out a much more powerful mathematical tool. This slide really nails the trade-off, doesn't it? Drawing is great, it's intuitive, but it can get messy and, let's be honest, a little imprecise. The analytical method, our next tool, trades that intuition for dead-on precision. It gives you the exact right answer every single time. So, the key to this whole analytical method is a seriously powerful idea called resolution. The concept is actually pretty simple. Instead of dealing with all these messy diagonal forces, we're going to break each one down into two clean, simple components, a pure horizontal part and a pure vertical part. It's kind of like giving a location its north, south, and east-west coordinates. I mean, just look at this thing. Imagine trying to add a whole bunch of diagonal forces, like this one. The geometry, the trigonometry, it gets complicated really, really fast. It's just not practical. But watch this. And this is where the magic happens. We can trade that one tricky diagonal force for two incredibly simple ones, a horizontal component, Fx, and a vertical component, Fy. This is the key, you guys. This unlocks pretty much any force problem you can imagine. And here's where it all becomes simple arithmetic. Once every single force is resolved into its x and y components, you just add them up. Look at the table here. We can totally ignore the original angles now and just sum up that x component column to get our total horizontal force, Rx. Then we do the exact same thing for the y component column to get Ry. all of a sudden, a complex geometry puzzle becomes simple addition. So far, we've only been talking about forces that push or pull in a straight line. But what happens if a force is applied a little bit off-center and it tries to make an object spin? Well, this introduces a whole new and really critical concept. This turning effect is called a moment, or you might know it better as torque. It's what you're creating every single time you use a wrench to tighten a bolt or a pry bar to lift something heavy. And the calculation for it is beautifully simple. The moment is just the force you apply multiplied by the perpendicular distance from the pivot point. That's the key part. And it's why a longer wrench makes the job so much easier. You're increasing that distance, which multiplies your force. All right, it's time to put all of our tools together on the workbench. We've got our classifications, we've got our geometry tricks, our analytical components, and this idea of moments. Let's see how they all combine to solve pretty much any problem we throw at them. So here it is, the complete problem solver's method. Step 1, resolve every single force into its x and y bits. Steps 2 and 3 are easy. Sum all the x's, and then sum all the y's. Step 4, you combine those totals to find the final resultant force. And then the final piece of the puzzle, step 5, you use moments to locate exactly where on the object that force acts. This 5-step process is the key to taming the chaos. And with this toolkit, you can now see the world like an engineer. You can start to analyze that invisible architecture that's holding everything together. I mean, even right now, as you sit there, you are in a perfect state of equilibrium. The force of gravity is pulling you down, and it's being met by an equal and opposite force from your chair, pushing you right back up. You're in balance, and now you know why.